Hello, everyone. Welcome to this slightly corrected version of Math 336, Mathematical Statistics, March 26th lecture. Unfortunately, I must have run into some trouble when videotaping the previous lecture, so everything about from the 6-minute mark to the end, I'm going to replace by this video. All right, so this is the part of the video where we're going to talk about testing whether two distributions are equal. So we don't have the time to talk about all that today. So we're going to at least ask, what if we have two distributions that are maybe shifted, maybe not shifted? Do they have the same median? So let's suppose that we have two distributions with CDFs F and G. F is for the X distribution, G is for the Y distribution. So the shape of their cumulative distribution functions is the same, but maybe one's been shifted to the right, which we see right here. Maybe it's been shifted to the right, maybe it's been shifted to the left. So how can we test this? Well, how do we test whether our distributions are in the same location or maybe one's been shifted? There are a lot of cases where this might come up. A lot of times when you compare men versus women, maybe there's some shift that's occurring and you want to know whether that's occurring or not, and you want some statistical way of testing that. Okay, so we create a combined sample. We take a sample of the X values and a sample of the Y values, and we write them in increasing order of magnitude, comparing or keeping track of which ones came from the X distribution, which ones came from the Y distribution. So we'll do that in a second on Excel, and you'll see how that works. So what we do is we take those samples that we took and we assign ranks to them. 1 is for the smallest, 2 is for the next smallest, all the way up to n plus 1 plus, n sub 1 plus n sub 2, right here. So we write their ranks. 1's the smallest, n1 plus n2 is the biggest. In the case of ties, you take all the numbers that tied and you average their ranks that you would have given them, and you give them all the same ranks. And you let W equal the sum of the ranks of just the Y values. So once we ranked them all, we kept track of which ones came from the X distribution and which ones came from the Y distribution. And we're going to add the ranks of the ones from the Y distribution. So if Y were shifted to the right of X, we would expect W to be larger than if they had the same median, because what's happened is maybe you've got this distribution where here's your X distribution, and you shift it to the right, and you get your Y distribution. This could be Y, and the red one could be X, and you would see that you would expect the Y values to be bigger than the X values. W is adding up the ranks of the Y values, so you would expect W to be big. So we're going to let MX be the median of X and My be the median of Y. And we're going to test the null hypothesis that the median is the same against the alternate hypothesis that the median of X is smaller than the median of Y. There is an assumption going on here in our work, and we're assuming that X and Y have the same distribution, but they could have different spreads. Okay, so our critical region is we're going to say if W is too big, then we're going to reject the null hypothesis and accept the alternate hypothesis. But the question is always, what value should we reject at? So in order to do that, we're not going to go through the derivation. It's kind of complicated, but if our samples both have size at least 7, and there are no ties, we can actually use a normal approximation to figure out how big W should be before we reject. So under the null hypothesis, you see this thing I've circled right here. This is the assumption of our null hypothesis that the X distribution and the Y distribution are the same. We get a normal distribution with this mean and this median, or sorry, excuse me, this mean and this variance, where N1 is the sample of the X values and N2 is the sample size of the Y values. Therefore, to reiterate, that means that our standard normal variable z is equal to this lovely quotient right there that you see at the bottom of the page. And that quotient should be approximately normal because we've taken w, subtracted off the mean, and divided by the standard deviation, like we do many, many times. That's what we do for things that are normally approximated. So just like before, the continuity correction is 1. It's not a half, it's 1. And we can talk about that more in class, why that is. So we're going to run through this all using failure times of light bulbs. So we have light bulbs from company X and company Y, and we've recorded how long do these light bulbs last in hundreds of hours before they fail. And you want to know, do the bulbs from company X last longer, or do the bulbs from company Y last longer? So let's take a look at our data. So let's change the share. Let's see, let's share Excel. All right. So here you see the X values. The X values are how long the light bulbs lasted from company X, and the Y values are the ones that came from company Y. So what you want to do is you want to take this column and you want to sort it. You always expand the selection, but we want to sort it by column B. And what happens is you see that you can assign ranks. So this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So in this right column, let's put up the ranks of just the Y light bulbs. These are the light bulbs that came from company Y. And we want to add them up. And we get 145. So this is how we find our W statistic. We've added up the ranks of the light bulbs that came from company Y. All right, well, let's switch back over to here, and you'll see what we saw earlier. W is 145. Therefore, to compute the p-value of our test, we find the probability that W is bigger than 145, and the continuity correction tells us that that's the same as W is bigger than 144. And we compute this z-score. Remember that in our sample before, N1 was equal to 10, and N2 is equal to 10. That is, we had 10 elements from company X and 10 light bulbs from company Y. And if we calculate that giant quotient, that's very lovely, we get a z-score of 2.95. So we can go over to our handy dandy, our studio. And we can compute this using 1 minus p norm of 2.95, and we get a p-value of 0.0016. That's really small. So our null hypothesis was that mu x was equal to mx was equal to my, and our alternate hypothesis was that mx was less than my. And when you get a p-value that's as small as 0.0016, you are always going to reject the null hypothesis in favor of the alternate hypothesis. In the case where maybe you wanted to do the two-sided alternate hypothesis, you just multiply the p-value by 2 because you get both tails. All right. So now we have a hypothesis test that tells us that we're pretty sure that the median of y is bigger than the median of x. But when you're doing statistical analysis, you don't just do one test. You do everything you can. You do the test, and you look at the graphical depiction. A good graphical depiction is very helpful, And the statistical test is to give you some level of probability knowledge about how likely or unlikely was something occurring. Pictures can be deceiving, but a picture in conjunction with the correct hypothesis test is usually pretty good summary of the information. So let's go back to RStudio. And when you're comparing two populations, you almost always want to use something like a side-by-side box plot. So we have a side-by-side box plot here. And if I annotate this, I see that this is data X, and this is data Y. And what do I notice? That it's true that the Y values look like they are definitely shifted from the X values. You see here, this is about, well, we threw out an outlier, so we get rid of our outlier. This over here is the minimum of the Y's, and that comes in at about Q3 for the X values. So whenever the minimum of your Y distribution, throw out the outlier, is about the same as Q3 for your X distribution, obviously the Y distribution has a bigger median. Here you have the max of the X distribution, and here you have the median, or Q2. And so what you see is that this graphical depiction of the data plus your hypothesis test together give you a pretty good, solid foundation for which you can say light bulbs from company Y, the median time they last is longer than company X. And obviously, if you want to say how much longer, you need some kind of confidence interval. Let me know if you have any questions. I apologize for the slight video mix-up. Take care.